My name is Lucas Ferrari, and today I'm going to be presenting my science fair project. For this project, I did an engineering project, where I attempted to build a model rocket that could launch and then land itself vertically without using a parachute. The way I decided to go about this was inspired by the motion of samara seeds. It's those little seeds that fall in the autumn that make a little spinning motion as they fall down from maple trees. This inspired the design of my rocket, which was a rocket that could launch like this, and then when it reached the top of its flight, these blades would deploy from the sides. And then it would develop lift through the concept of auto-rotation, which is already well known and used in helicopters, to spin itself slowly to the ground and land safely. If applied to the larger scale space industry, this would help save millions in overhead costs from launching rockets and then having them disintegrate in the atmosphere. Now, other companies have tried different ways of doing this, but I think my way is unique out of all of them, in that it uses the spinning motion of the rocket itself to land, instead of using retro rockets or a parachute. This project is actually a continuation of a project I did last year, where I attempted a similar goal with a rocket that looked like this. Now, this rocket isn't the best designed, I'll admit, and it didn't perform at all. That's the end of the sentence. It crashed and it actually hit my dad's truck, which meant that it wasn't able to fulfill the goal that I designed it for. So I decided to try it again this year with a little bit more time on my hands, since I had run it down close to the wire last year, and I could spend some more time on developing and actually trying to test this rocket before I just launched it. So I'm going to show you a video of my first test that I did on this year's rocket, which was a drone test, where basically I hooked it up to a drone, flew it way up into the sky, and then released the rocket when the drone was at its highest, when it was at its maximum height. So there's the release, and the rocket falls, and it hits the ground. So the problem with this test, I think, is that I wasn't able to get the rocket high enough as to where the blade spinning would be effective in landing it. It got itself up a little bit, and then it began to recover, but before it could fully swing back around to begin spinning, it impacted the ground. This was much better than last year's rocket, which I actually rebuilt and flew again for this year. I wanted to see if last year's design had any merit to it, because if I went through all the work of rebuilding it when I could have one this year that worked perfectly fine, then what was the point? So here's the video of last year's rocket rebuilt doing a launch. And there's the ejection charge. That explosion at the end is supposed to be the explosion that ejects the blades and allows it to begin spinning down to the earth. But it didn't eject until it was already on the ground. Well, why is that? Well, this rocket was grossly overweight for the size of the motors I put in it. It weighed somewhere around 140 grams, while the rocket motor is only rated for about 80 or 86 grams. So not only was it too heavy, it spun in pirouettes and then hit the ground, but I think it did much worse than this year's, which is why I think this year's rocket is a success over last year's. So here is a video of this year's test. And there's the ejection charge. Now, a similar problem from last year. I decided to look a little bit more in depth into this rocket, and I realized that not only was it overweight and underpowered, but it was also incredibly unbalanced. Nothing was where it should be, from the center of gravity to the center of thrust to any of the calibrations in terms of rocket physics. It just wasn't right. Nothing about it worked right. But it was able to make it higher into the air and travel a further distance than last year's rocket, I mean. And I think the design from this year's was a lot more sound in terms of actually functioning. Because when it did hit the ground and the ejection charge went off, it was actually able to perform its function. Well, what was its function? So here I have a diagram of the innards of this year's rocket. I had a friend 3D print out all of these pieces here, and this is actually just a diagram of the 3D printed pieces, which I designed in the 3D modeling software Autodesk Inventor. So what's intended to happen when the rocket reaches the top of its flight and the ejection charge goes off is it's supposed to hit these actuators here in the center. These actuators lift up, which in turn pushes down these hooks here at the ends of the tips of the wings. When this happens, the expansion of the charge continues up into the chamber, which pushes out the blades here, which provides the kick that it needs, and in addition, around here there are rubber bands tied to the edges of these actuators at the top. This means that when the ejection charge goes off here in the bottom, it lifts up these little levers inside here, which then pull out on these wingtips, which then in turn lead to the blades ejecting like that. Now, to give you a sense of how well the crash went, here are what are supposed to be the wings attached to the inside of the fuselage here. A couple of them broke off in the crash, and I decided to just tear off the rest. Because I actually launched this rocket as it was bare bones, just for fun, mainly. I wanted to see how it would do when I had eliminated all the weight from it. It crashed even more spectacularly than the first time. So I don't think that... I believe that this project was a success in terms of it performed better than last year's rocket, which, when you're doing a continuation of a project, is a good sign that you're onto something. But given the two failures in the actual deployment of the mechanism, I believe that this should be well left alone for now. Thank you for listening for my presentation.